Log on, tune in, find out. Another good idea from Cambridge.
Hi, okay. It's a great pleasure to introduce the next speaker, Eric Optam, who will speak about the spectral transfer category of affine Hecke algebras.
Thank you very much, Meinhof. It's a great pleasure to be here, and I thank the organizers for the wonderful environment they've created here. And it's really a pleasure to work here. Yes, so my talk today, of course, involves, as you can judge from the title, it involves some analysis, because it's about spectral theory of Hecke algebras. So in this audience, maybe I should start with an apology for that. So what I would like to explain is that, well, maybe still about this remark, even though it seems to be very analytic, maybe at first from the definitions, there is harmonic analysis and measure theory involved, all objects turn out to be algebraic in the end. So all the things that you compute are rational functions with only cyclotomic factors. And so it is really an algebraic theory, but I don't know how to formulate things or how to do things purely in algebra yet. Okay, so that's one remark. What I would like to describe is that if you look at the spectral theory of Hecke algebras, then sometimes these spectral theories, even though the data defining the Hecke algebras is completely different, can be completely different root systems like E8 and F4, and the parameters are completely different, still the spectral theory has a huge, is very intimately related. And this phenomenon I would like to explain, and for that we need a new type of maps between Hecke algebras, which are not given by algebra maps, but rather you have to go to the spectral side and define a new notion, which I call a spectral transfer map. And then we will apply it, after this, we will apply this to the classification of unipotent representations, which was done by Lustig already a long time ago. And so we will understand his results from the perspective of harmonic analysis. And so that is interesting because it has also a natural meaning in terms of harmonic analysis of p-adic groups. And so this is, it's nice to connect Lustig's geometric world with the harmonic analysis directly. And then what I maybe should say is that some version of this already existed by the work of Mark Reeder for small rank groups. And in some sense, I extended or I introduced this new notion of a spectral transfer map in order to be able to also do this type of understanding in groups that are really large, I mean for classical groups. And well, for that one needs to change a little bit the perspective that Mark Reeder had on this. And so, well, we will see this as we go along. But okay, let's start with the just the definition and the notations related to affine Hecke algebras. So we start from an affine Coxeter group with a set of generators S naught up to Sn. So I assume S for this talk to be irreducible. So it's a connected diagram. And then I work over some ring lambda. It's a Laurent polynomial ring in one variables as the base ring. And then the Hecke algebra over that ring lambda is, well, generated by elements indexed by the elements of S, the affine simple generators of my affine Weil group, with the usual relations, the braid relations and the Hecke relations that probably in this audience everybody knows very well. But just to fix the notation, so I have certain integers mi that show up in these Hecke relations, and they of course should satisfy this rule that if two simple generators in the affine Weil group are conjugate, then the mi should be the same. And then it is a classical result that this is a free algebra over the ring lambda, which has a distinguished basis NW, where W runs over the elements of the affine Weil group. And in fact, these NWs can be constructed by taking a reduced word in the affine Weil group and then multiply the corresponding simple generators. And that's independent of the chosen reduced word. And well, here it is already clear that we are not doing algebra, because now I will introduce an antilinear anti-involution, complex antilinear. And well, it is defined on the basis by saying that NW star is NW inverse, and then one can check that this is really extending to an anti-involution to the whole Hecke algebra. And on the parameter V, well, the parameter is real according to this formula. Now, this star structure I introduced is already an important ingredient for the type of harmonic analysis that I would like to associate with an affine Hecke algebra. But also I need a trace, which is normalized in a very special way. So, well, I call it the square of V, usually Q. That will make it easy to relate it to the applications in periodic groups later on. K, capital K here will be the quotient field of lambda, and I choose an element D to normalize the traces for different values of V by an element little d, and that should be an element of the subgroup of the multiplicative group of K generated by the rational constants, by power by Q, and by cyclotomic polynomials. And moreover, it should satisfy certain positivity condition, namely for a substitution of V bigger than 1, this thing should be positive. And so then at such a specialization it should lead to a positive trace. And also there should be this symmetry. And well, the first proposition towards the harmonic analysis in this situation is that such a linear functional with respect to the star operator that I introduced here is positive for all specializations of the parameter larger than 1. And in fact, this positive trace together with the star makes the Hecke algebra a Hilbert algebra. And that means that the left and right regular representation of the Hecke algebra is through bounded operators with respect to the natural Hilbert structure that you get from this trace and star. So the inner product, I didn't write it down, but the inner product, of course, is H1, H2 is the trace of H1, H2. So that defines a Hilbert structure in which the NWs are orthogonal, and the action of the Hecke algebra on itself is by bounded linear operators. And so we can take now the C star completion of the Hecke algebra with respect to the operator norm in this Hilbert structure. And that gives us a C-star algebra. And so that C-star algebra is called C of V, where V is a special value of the parameter. It's the C-star algebra completion of the Hecke algebra. And if we denote by capital sigma of V the irreducible spectrum of this C-star algebra, which we also will call the tempered spectrum of the Hecke algebra, then well, we can embed this in the irreducible spectrum of the Hecke algebra by just restricting. So if a module is a irreducible module for this C-star completion, and then you can restrict it to the Hecke algebra, it's easy to prove in this context that you get an irreducible module of the Hecke algebra. And so you have a certain subset of irreducible representations of the Hecke algebra that have a continuous extension to the C-star completion. And this is called the tempered spectrum. And we denote it by this capital sigma of V at the special value of the parameter V bar. And well, this C-star algebra is really very nice. So it's an old theorem of Matsumoto that it is a type 1 C-star algebra. And as a corollary, one can apply the Dixmier machinery to get a Plancherel decomposition of the trace. So there exists a unique positive measure on the tempered spectrum, and this measure is what we call the Plancherel measure at the specialized parameter V, writing the trace as a superposition of irreducible characters which are tempered. Okay, so that is the definition of the Plancherel measure. This Plancherel measure is directly related to the Plancherel measure of p-adic groups restricted to Bernstein blocks that are described by Hecke algebras. And so it is a really interesting quantity to compute. And as I said, although this definition is of course entirely from analysis, the Plancherel measures, if you compute them, are completely algebraic functions. They are rational functions in everything what you would like to consider. Not only rational functions, but also rational functions with rational coefficients. So now I need to talk a little bit. So this measure was defined at a specialization, so at V bar, a specialization of the parameter. But as I already said, I would like to make a very precise normalization of the measures at the different specializations. This is really important in this setup. So I have to talk a little bit about the vibration over R bigger 1 of the spectrum. So of course the Hecke algebra, if we purely consider it algebraically, it is a lambda algebra, so there exists a vibration of the irreducible spectrum over the maximal spectrum of lambda, which is C star. But this is very, very complicated. But if you restrict to the numbers are larger than 1, then this simplifies very much. And in fact, one can show, this is a result of Lustig, using reductions by going to formal completions of Hecke algebras to graded affine Hecke algebras. One can show that there are natural bijections given two parameters which are bigger than 1. There is a natural bijection between the irreducible spectra of these two Hecke algebras. Even though it is not true globally that these Hecke algebras are isomorphic, but locally, if you take formal completions at central characters, this is revealed. And these are called scaling maps. But we are interested in the harmonic analysis, so we want to also understand what these scaling maps do on the level of our tempered spectrum. And this is a result of Solleveld, that everything behaves very nicely. His first result is that scaling maps induce homeomorphisms on the tempered spectrum, where the tempered spectrum is given the Jacobson topology that you would give to the spectrum of a C-star algebra, which it is. And in fact, there exists a trivial bundle of C-star algebras over this base, R bigger 1, with fiber equal to the specialized, to the C-star completion of the specialization. And so that immediately implies that there exists, if you look at the spectrum of this bundle of C-star algebras, we call that capital sigma, you get a certain topological space which is fibered over R larger 1, and this fibration is trivial and has fiber precisely the spectrum of the C-star completion of H at nu bar. And so we can associate to a given Hecke algebra defined over lambda, we can associate to that a family of Plancherel measures which live on these fibers. And so this family of measures I call the Plancherel measure. And so then I remind you that my tau here, this trace, was very carefully normalized by this element D, which is in this subgroup M of the multiplicative group of the quotient field of lambda. So we have, if we speak of the Plancherel measure, really I speak of a whole family of Plancherel measures at once. And this is really crucial to do in this context. Another ingredient that is really important to understand something about the representation theory of affine Hecke algebras is the central character map. So we take the subgroup of the affine Weil group consisting of all those elements which have only finitely many conjugates. This is a normal subgroup, and it is the lattice subgroup of the affine Weil group, the translation lattice. And it has a complement, which is the finite Weil group W0, which is generated by the finite generators in S. And then we know that we have this nice semi-direct product decomposition of the affine Weil group. And then it follows from the work of Bernstein that this semi-direct product decomposition really exists also on the level of the affine Hecke algebra, which one can view after all as a deformation of the group ring of the affine Weil group. And from that one can see rather easily that the center of the affine Hecke algebra must be isomorphic to the group ring of the translation lattice X, and in there the Weil group invariant elements. And the Hecke algebra is consequently of finite type over this center. And so as a corollary of that, one sees that one gets a central character map, which is a finite surjective map from the irreducible spectrum to the maximal spectrum of this center. And so here T denotes an algebraic torus whose character lattice is the translation lattice of the Weil group times Z, and Z here accommodates the indeterminate V of the ring lambda. And now we want to understand how this restricts to the tempered spectrum. So I define curly S to be the image under the central character map of the tempered spectrum sigma. And I equip this with the analytic topology as a subset of my complex torus. And then one can say that, if we call the restriction of the central character map to sigma, from sigma to S, we call this the tempered central character map. This is a finite and continuous map. And so S here is the central support of the tempered spectrum. Both, of course, lie fibered over R bigger than 1. And also, what is important in this situation is that there exist open dense subsets of the tempered spectrum and the support of the tempered spectrum, such that if you restrict your central character map to that, you just get a finite covering of smooth manifolds. Okay, enough about that. So then I think everything is ready to introduce these spectral transfer morphisms. So we have now a normalized affine Hecke algebra. It consists of an affine Hecke algebra defined over lambda and an element D normalizing the trace in the family of specializations as before. Well, such an object is completely determined by its mu function, its McDonald-Harishchandra mu function. Because, well, this is well known. One can also introduce affine Hecke algebras from an affine root datum with some parameters on the affine root datum and then construct it through the Bernstein presentation of affine Hecke algebras starting from this. But that is sort of a dual description, and all the information one needs for this dual description is hidden in this so-called mu function. And the mu function is written here. It's a rather intimidating expression, but okay, I wrote it down anyway. So it's completely factored in these typical factors. 1 minus a character on the torus. And it's a rational function on this torus T. It's Weil-group invariant. And what are the different ingredients? You see some parameters m plus and m minus showing up. They live on the finite root system. And they are half integral valued. And subject to certain conditions. Again, it should be Weil-group invariant, and if you add m plus and m minus for every root, you should get an integral value. And then there is this function nw0. It's basically, well, it is what you get if you restrict your parameter defined on the affine Weil group if you evaluate that on the longest element in the finite Weil group. So then you get q to the power this mw0, or v to the power 2 times that. And so then here is this d, which we use to normalize our trace. It shows up in the mu function also. And okay, it's a product over all these roots of these elementary rational functions. And it contains, again, it's a very important point, it contains all the information to recover the Hecke algebra up to isomorphisms. Now, what is a spectral transfer morphism? Yes, 1 plus. And in the second one minus, yes. So a spectral transfer morphism is from H1 D1 to H2 D2. It's an equivalence class of affine morphisms, but forget about the equivalence for now. It's given by an affine morphism between the tori T1 and T2 associated to the Hecke algebras H1 and H2 with the following properties. First of all, it should be a finite map. So the dimension of the image is just the dimension, it's the rank of the first Hecke algebra. The next is a rather delicate condition. It says that the pole order of mu2, which is the Harishchandra, McDonald-Harishchandra function for the second Hecke algebra, along this image should be equal to the codimension of the image. And that is, in fact, that's the highest possible pole order that can occur. If you take any coset of an algebraic subtorus of T, and one looks at the mu function and computes in the denominator and the numerator the number of zeros, then the highest order that you can find of a pole is what I wrote there, the codimension. That's a very special property of this mu function, and it's very non-trivial. But that is a necessary condition to, necessary fact to make this definition work. And finally, if we now regularize the second mu function along this image, and that means simply, well, one, for example, throws away all the terms in the numerator and the denominator which are 0 along this image, and then we take the pullback of this regularized mu function to the first torus, then one should get up to a complex number, a factor, one should get the mu function of the first Hecke algebra. That's it. And what does it mean for two such maps to be equivalent? That simply means that they are the image under the action of the second, of the Weil group of the second Hecke algebra. So this is, and so in general these maps are not corresponding to algebra maps. That's an important remark. If the dimension of H1 or the rank of H1 and the rank of H2 is equal, then there is an underlying algebra map, one can always show, corresponding to certain diagram isomorphisms. But otherwise, it is one can show that it is never given by an algebra map. All right, and then the first main property is the spectral correspondences that arise from such maps. So suppose that we are given such a spectral transfer morphism, then it induces, first of all, a map on the support, the central support of the tempered spectra. It's a finite continuous map, which I call the associated map phi of S from the support of the tempered spectrum of H1 to the support of the tempered spectrum of H2. And it maps components onto components. That's also a non-trivial fact. And the second point is the main, I guess. So we have now two maps to S2, the support of the tempered spectrum of H2. So this horizontal map is simply the central character map of the second Hecke algebra. But here we have a map from the tempered spectrum of the first Hecke algebra by its central character map to S1, and then we can compose it with this phi of S. And so you get another map to S2 from the spectrum of H1. And then we take the fibered product. That gives us a correspondence between the tempered spectra of H1 and H2. And the claim is that this correspondence behaves well with respect to components. So if you take a component of sigma 1, 2, then it is mapped by P1 and by P2 to a component of the tempered spectrum in H1 respectively H2. And there exists a positive measure on this fibered product such that the pullback of the Plancherel measures of sigma 1 and sigma 2 to sigma 1, 2 is up to a rational constant the same. So there exists this nu 1, 2. So suppose that we have two components here which are the image of a component C1, 2 in sigma 1, 2. So then there exists a positive measure on C1, 2 and the rational numbers A1 and A2 such that these pullbacks of the Plancherel measure, no, sorry, I'm talking about pullbacks, but I should, of course, in the case of measures, take push forwards. So I'm very sorry. So you take the push forward of this measure here to sigma 1 and to sigma 2, and it gives you up to these rational numbers the Plancherel measure of H1 and H2. So in short, this spectral transfer morphism between the Hecke algebras induces a Plancherel measure preserving correspondence up to locally constant rational factors between the tempered spectrum of H1 and H2. Moreover, it is surjective, this map, on it's surjective on on the tempered spectrum of H1. I forgot to write that, but that's an important property of this correspondence. So now so that is the basic definition and basic property of these morphisms. Now I would like to apply this to the unipotent representations for p-aric reductive groups that Lustig has defined. So there is a very important and beautiful paper of Lustig classifying the unipotent representations. And it turns out to be as expected. So what comes out of it is that really one should think of the unipotent representations as being, if you look at the local Langlands correspondence, it should be corresponding to the unramified representations of the Galois group, of the V group. And so now I would like to use my spectral correspondences to understand the picture that emerges from his work in the context of harmonic analysis. So we need to go over some, over this context and fix some notations. So that is, but that is maybe in this audience not the biggest problem. So we have a non-Archimedean local field, little k, and a connected split simple algebraic group defined over that, which is of adjoint type. And capital K, and now I see I made a mistake because in the previous part capital K was the quotient field of lambda, and I didn't intend this coincidence, so I apologize for that. I see that only now. So capital K here is the maximal unramified extension of little k. And it has nothing to do with the k of the previous part. So its Galois group over little k is the profinite completion of Z. And we take G to be the capital K points of G bar. And we take an Iwahori subgroup of that group. What is an Iwahori subgroup? Well, I think everybody in this audience knows, but anyway. So we take the residue field of K bar, and then there is the reduction homomorphism to this group over K bar, to the points over K bar of this group. And then you take a Borel B bar in this group over K bar, and one takes the inverse under the reduction homomorphism of that. Now, why do I want to work over capital K? It is because I would like to consider all unramified extensions of small k at the same time as a family. And this is the same family that I carefully kept all the way through the definition of the spectral transfer morphisms. It's the same thing. And now we take the group GF, that is our locally compact p-aric group. It's just now the little k points of G bar. And we fix a Haar measure on that by by insisting that the volume of the Iwahori in that GF is 1. The Hecke algebra of GF is by definition the convolution algebra of locally constant, compactly supported functions on this locally compact topological group. And that is also an algebra equipped with a star, naturally. The star is written there. And then, of course, there is the category of smooth representations of the Pierre group, which is simply nothing else than the non-degenerate modules over this Hecke algebra. So, there is a spot. Oh, okay. So, well, then there is an really a result of basic importance to the harmonic analysis of GF of the Pierre group. And this is the Bernstein decomposition. But I am not going into any detail here, but there exists a natural decomposition of the category of smooth representations of GF as a product over the so-called Bernstein blocks. It's a countable, usually countable product. And the set of parameters, the index set of these blocks, is the set of components of the Bernstein variety. And so I denote by this category RG of F of S, the corresponding Bernstein block corresponding to a component in the Bernstein variety. And well, these are blocks, so full abelian subcategories. And Lustig has now defined his unipotent representations by singling out a collection of components of the Bernstein variety, which one might call unipotent. And it's a finite set of components. This finite subset I call BGFU. It's the unipotent, the set of unipotent components in the Bernstein variety. And it is impossible in the context of one such lecture to say anything about this in technical detail, but I can give you as a sort of, I can describe the landscape a little bit. So what are the properties of, and what is the okay, I will try to say step by step what these unipotent components, what kind of properties they have. First of all, it's invariant undertaking unramified extensions. This is so there is a natural way to identify if one goes to an unramified extension. So this set B GF of U, this is a finite set of components which we can fix over capital K. For each component, one can find, so now there is the definition actually of this component, one could say. So Lustig's description is as follows. If we have such a component, then, well, it's maybe, I should say it the other way around. So we start from a parahoric subgroup, PS of F in GF. It's compact open, but it is more than that. It is a parahoric subgroup. And we take an irreducible representation of that, but not just any one. We take a cuspidal unipotent representation. So that means there is a representation of the Levy quotient of this parahoric subgroup which is cuspidal unipotent in the sense of Lustig's theory of characters of finite groups of Lie type, and that we inflate to the parahoric. That is my sigma s. And then if one looks at the category of representations of GF which are generated by their sigma s isotypical part, then this turns out to define a block in the Bernstein decomposition. This is a very non-trivial fact related to the properties of cuspidal unipotent representations. And it is a far-reaching generalization of Borel's theorem, saying that one can describe the block in the smooth representations generated by the minimal unramified principal series precisely by the property that they should be generated by their Iwahori fixed part. So that is a special case. It is the Borel case. Maybe I should give it a special attention. So if we take BF for PF and then sigma is the trivial representation. That is a special pair, and it corresponds to a component in the Bernstein spectrum, which is the Borel component. And so the irreducibles in this component are precisely the subquotients of the unramified minimal principal series. The subquotients. Of the unramified minimal. So this is Borel's theory. But it is very remarkable, because if one takes just any compact open subgroup and any representation of that, and one looks at representations defined in a similar way, then usually it is not at all closed for taking subrepresentations. So it's not a block in general. So, okay, this is, so now we take all possible pairs like this. So we have a parahoric and we have such a cuspidal unipotent representation. And then what I just said amounts to saying that to each such pair there corresponds a block in the Bernstein decomposition. And this block is BFGU. And then there is a Morita equivalence between this block and the representation category of the Hecke algebra. Which Hecke algebra? Well, I didn't write that formula, but I can do it on the blackboard. So we have the Hecke algebra associated to this and sigma s. So this, I think I made a different notation here. Ah, there is a GF here. This is by definition the locally constant compactly supported functions with values in the endomorphism ring of sigma s. Of set, say, E sigma s. This is the space on which realized such that they transform under sigma s from the left and the right. So we have f p1 g p2 is sigma s p1 fg. And this is, of course, also the endomorphism algebra of the induced representation. So this is also, that's another way of saying it. It is the endomorphisms over G of the C induced from P. And this Hecke algebra acts on the isotypical part transforming under sigma s of the representation. So we have now this mapping a representation in this block to its isotypical part, and that gives us, starting from a smooth representation in this block, gives us a Hecke algebra representation. And in fact, the next important statement, which is also tremendously surprising, is that for all these unipotent components, all these Hecke algebras that were written down by Lustig are in fact on the nose affine Hecke algebras as we introduced it before, specialized at v squared is equal to q, where q is the cardinality of the residue field of little k. So we have now a whole cloud of affine Hecke algebras which together describe the unipotent representations. So the category of unipotent representations is just this product of all these finitely many blocks, as I just described. And then Lustig's result is the classification of these unipotent representations. Well, there is one obvious way of classifying these representations which is almost direct from the definition. Namely, this is, as we discussed here, it's just a product of these module categories of these Hecke algebras. And so one can say, okay, if we take all the irreducibles of these Hecke algebras together, then together this should be in bijection with the irreducibles that are unipotent. But then there is his very non-trivial theorem that there is a completely different way of parametrizing the same set of irreducibles in terms of Langlands parameters. So now we look at G check. It is the Langlands dual group of G. And we look at all the Langlands parameters, so which are unramified. So we take a representation of Z, that's what remains of the W group after taking the quotient by the inertia group, because we are just looking at unramified representations, times SL2C. And so landing in G check up to a conjugation by G check. And here, for every such parameter, one has to then take the irreducible representations of the component group of the centralizer of the image, not the center. And for many of you is probably the most famous statement along these lines, where one has to make a restriction on these representations of the component group, namely if one wants to describe only the representations that correspond to this Borel component. So then we are only looking at the Iwahori Hecke algebra, because that is the one, of course, obviously, which corresponds to this block. Then one has to say, okay, this representation in this of this component group has to be special, it has to be geometric. That is the additional condition. But now, if we look at the world of all unipotent representations, then it's not anymore restricted in this sense. It's still restricted by saying that, well, the center has to act trivial, but that's related to another phenomenon which is well under control. It's just because we work with split groups. And I think the whole setup works equally well generalizing this, but I haven't just gotten around to doing that. Okay, so this is his result. And now I would like to approach this using the harmonic analysis of these Hecke algebras and how they fit into each other. So then the first thing that should be remarked is that if we look at the Morita equivalence that we just defined from the category of unipotent representations of the p-aric group to this product of module categories of this whole cloud of affine Hecke algebras, that map can be made compatible in a unique way with the harmonic analysis. What does that mean? Well, that means that it is mapping tempered representations to tempered representations. So here I have a natural notion of tempered, but for Hecke algebras I previously introduced that. And under this correspondence, the Plancherel measures correspond to each other, up to rational constants. Well, one can normalize things so that it really on the nose is correct. And this is a result due to, well, it was a remark of Heckman and myself, and later it was worked out by Bushnell and Henninger in Kutsko in great technical detail. This is yes, correct. This is a statement for the first line. You are right. But I'm going towards the second line. So the first theorem that is quite striking is that there exists an essentially unique spectral transfer morphism from this whole cloud of unipotent Hecke algebras to the one associated to the Borel component. So these strange conditions on the mu functions corresponding, so one has to have this pole condition and then the pullback of one mu function should be the other. It really makes, well, it's very remarkable. All the Hecke algebras that you find in this unipotent world of Lustig, they have a unique map to the Iwahori-Matsumoto algebra in this sense. And the next result is, well, it's what you would then expect, but one can verify it explicitly also using the work I did with Maarten Solleveld on the classification of tempered representations of Hecke algebras for unequal parameters. So if we now take, for example, the case of L2 representation, so then we should look for local Langlands parameters that are not only unramified but also discrete, which means that the centralizer of the image is finite. Then they should correspond to the discrete series representations. And now, given such a parameter, the Kasdan-Lustig classification of representations of the Iwahori-Matsumoto Hecke algebra, where the parameters are equal, leads to a central character associated naturally to one such parameter. The central character I call psi, depends on this phi. And that is, if one takes all the discrete unramified local Langlands parameters, one gets precisely under this map all the central characters of the Iwahori-Matsumoto Hecke algebra that support L2 representations. This is well known, it's in their paper. Now I look at the inverse image of, so this psi under the map phi of S, which is the map induced on the supports of the tempered spectra by this unique spectral transfer morphism, there is a element. I look at all the possible psi of S in their support, in the corresponding support of the tempered spectrum of that Hecke algebra, which map to this psi, where psi is one of these guys. And I take all the tempered representations that lie above that with the central character map, and then I take the union over all the components in the unipotent components that one has to associate to G of F. And then beta was the Morita equivalence that goes from Hecke modules to the modules of the G of F. Then it turns out that this is a packet of representations, and if one computes simply, it's a after all this work, a rather simple computation. If one computes the number of representations that one gets, then this is precisely the number that is predicted by the local Lagrange correspondence. So you get precisely the number of irreducible representations of the corresponding component group on which the center is trivial. And so in a sense, this is the direct equivalent of Lustig's result, but now formulated entirely in terms of harmonic analysis. And of course one gets now, because of theorem 1, because of these spectral correspondences, we get immediately the result that within such a packet of representations, all the formal degrees are equal up to rational constants. So I would like to make some comments at this point. So for exceptional groups, this approach was very much promoted by Mark Reeder, or yeah, he looked at this but didn't have a very efficient way to compute the formal degrees. Later, a result of Heckman and myself helped to at least see what the formula for the formal degree should be, and that gave new fuel to his method of understanding the Lagrange correspondence in this way. And then he could do it for all exceptional groups. But he has a different way of matching representations. So the notion of a spectral transfer morphism didn't exist because he is just comparing the formal degrees of L2 representations. And he never looked at the mu function. So in some sense my definition involves the most continuous part of the spectrum, and there I try to match the measures, and I show in theorem 1 that then the way he looked at it is a consequence of that. But it is very important to look at the most continuous part of the spectrum because it makes the theory very computable. So I will put up the next slide, I will do it for the odd orthogonal groups, and then you can see how this category, what the structure is of this category, this spectral category of Hecke algebras. It's a very simple thing. Another remark is that really what's making this tick is this beautiful property of the mu function, that the pole orders along any coset of an algebraic subtorus is never exceeding the codimension. And this is well, I have a conceptual proof of that now, but it's not a simple proof. And also in the case where the parameters are all equal, this is not at all a simple matter. Then I think it is a consequence of Richardson's dense orbit theory. Yeah, and also the results I claimed in theorem 3, that is based on joint work with Maarten Solleveld, where we, for all Hecke algebras, classified the discrete spectrum. So that is what you need in order to count these packets, of course. Yes, so of course the reader himself was inspired, I think, by or was guided by the conjectures of Shahidi regarding the behavior, the expected behavior of Plancherel measures within L packets. So this is, and finally, rather recently, there has been a lot of work towards the geometric models for affine Hecke algebra representations of type, I call it usually C1, the affine extension of Cn, C1n, by Kato, and in a later work with Chubotaru. And so they can get also internal information on the representations, although the correspondence between the geometric parameters, the exotic geometric parameters, and the tempered theory, the tempered representations, is not as natural as one finds in the Kastan-Lustig theory. Still, they have been able to work it out combinatorially, and they got quite non-trivial results on the k-types in the tempered modules. And that, I think, I hope, can help even to compute these rational numbers in the Plancherel measures that I so far have not been able. I've been able to prove that they are rational, but I have not been able to compute them. So for each root system there are finitely many rational constants to compute, and I really would like to do that because I think they are very meaningful. But so far I haven't been able to do that. But I think there is a new opportunity using Kato and Tubertaru's work. And then finally, I just made a sketch of the spectral category for the orthogonal groups. And what are the spectral morphisms? So the dots, the red dots are half integral points. And the shaded regions you shouldn't count because they do not correspond to Hecke algebras that show up for the orthogonal groups. But anyway, I include them in my spectral category because they serve to simplify the basic steps of which I can out of which I can compose any spectral transfer morphism. And well, so the spectral, so each red dot represents an infinite number of Hecke algebras because the rank is still a variable, but the m plus and m minus parameters are fixed. This is one of these half integral values. And then there are spectral transfer maps going down. They commute, and they are translations by one step in these letters downward. They are not invertible. And this you have to complement by the invertible spectral transfer morphism, which is the reflection in this line. And if one wants to combine all the Hecke algebras that come from one particular orthogonal group, let's say SO2n plus 1, there is an additional condition that the sum of the squares of these two parameters plus a half is the rank, is less or equal the rank. Yes, that's correct. Yes. But then the picture is different. So, I mean, if I would do the picture for SP, I don't know how it will change, but it changes definitely. Okay, and then what is nice about this theory is that the basic steps are just moving the parameter by one. They are just simple shift operators in the parameters of these Hecke algebras by step one. And although they do not have a direct meaning in the world of p-adic groups at all, they are extremely easy to compute everything in this category that one wants. So that is really very helpful. Thank you very much.
Do you hope to be able to prove stability of L packets of discrete series, for example, using this approach?
No, I believe that it is expected that if one knows the stability and some other expected properties, then such results would follow. At least one would also get from this analysis the fact that the formal degrees are equal up to rational constants. So this is expected, but I do not have any way to approach the stability from this perspective. But rather, what I did is use this expected property and more or less worked with the converse implication and showed that it really defines everything uniquely. It's a nice question, I think.
Let's thank the speaker again.